This talk is about an algorithm for efficiently and automatically finding high-performance implementations of Halide programs for the GPU. Halide is a language for high-performance image and tensor processing. The key idea of Halide is that every program is separated into two parts: the algorithm, which describes the high-level intention of what you want to compute, and the schedule, which describes how you want to compute it and specifies low-level implementation details like parallelism and storage. This makes it easy to write different schedules to explore different implementations of a given program. Using this approach, it's possible to obtain very high-performance implementations, which has led to Halide's adoption in industry at places like Google, Facebook, Adobe, and others. But even though it's easy to try different schedules, it's still difficult to actually find good schedules. This requires expertise in Halide, image processing, and program optimization. The goal of this project is to find high-performance schedules automatically. Let's look at an example program. Here we have a 3x3 box blur that works in two stages. First, blur X that operates on the columns of the image, then blur Y operates on the rows of blur X. In the bottom left, we have a possible schedule for this algorithm. You don't need to understand all the details, but these operations specify things like how much and where memory is allocated, and how loops are parallelized as GPU blocks and GPU threads. The Halide compiler then takes the algorithm and this schedule and generates a concrete loop nest implementation, which looks kind of like the code you would write if you were doing this manually in C or C++. The autoscheduler mostly operates on this kind of loop nest structure, so it'll be helpful for the rest of this talk to have in mind that a schedule corresponds to one of these concrete loop nest implementations. Now, this is just one possible implementation of this algorithm. If we want, we can edit the schedule to get a different implementation. In this case, we've just changed some numbers, and this creates a loop nest with the same structure, but different loop extents. We can also change the schedule more substantially to get a structurally very different loop nest. All of these options have different performance characteristics. They do more or less computation, use more or less memory, and use more or less parallelization. Now, these are just three possibilities, but algorithms typically have a very large space of potential schedules, often in the millions or even billions. So how do we find a good schedule from within this space? At a high level, we need to do two things. First, we need a way to enumerate possible schedules. This means valid schedules that compile and run. On the GPU, this means respecting the hardware limits of things like shared memory and the number of threads available. And because the space of schedules is so large, we can't simply enumerate everything. Instead, we want schedules that are plausibly good based on human knowledge. For example, selecting thread sizes that are multiples of 32 in the warp dimension. The second thing we need is a way to search the space. The major challenge here again is scalability. Even limiting the space to plausibly good schedules still produces too many options. And the major reason for this is that GPUs have nested parallelism. On the CPU, there is only one level of thread parallelism. So a major scheduling decision is, how large should the parallel thread loops be? But on the GPU, there are two levels. So there is a nested decision. How large should the block loops and thread loops be? This can lead to thousands of possible tiling options for a single stage of a pipeline. To deal with this, we need some way to search the space of schedules in a scalable way. Prior work doesn't address this challenge. Our previous autoscheduler is CPU only, and its algorithm doesn't handle nested parallelism well. The state-of-the-art Halide GPU autoscheduler restricts its search space to avoid nested decisions, but this excludes some important options. There are three key ideas to address these scalability challenges. First, we use a hierarchical sampling strategy. Instead of evaluating all scheduling options in the search space, we group schedules by structural similarity. From within each group, we sample candidate schedules and discard the rest. In doing so, we search the space, but only evaluate a subset of it. The second idea is to identify low-cost paths of the program and make coarse-grained decisions for them at the beginning of the autoscheduling process and freeze those decisions. We then spend relatively more time making decisions on the high-cost or important parts of the program. Third, we recognize that partial schedules frequently reoccur during the autoscheduling process. We want to amortize the cost associated with each partial schedule over all its occurrences. Here's the basic idea of how we schedule a Halide algorithm. We start with an unscheduled algorithm, and instead of trying to jump from the unscheduled algorithm directly to a fully scheduled loop nest implementation, We break the process up into a sequence of smaller decisions. We schedule each stage of the algorithm one by one. This creates a tree of decisions that we need to search over, and each entry in the tree is a partially scheduled loop nest. Before evaluating any of these options, we group them based on structural similarity. We sample representatives from each group and discard the rest. We use a learned cost model to predict the runtime of each partially scheduled loop nest, and we use a beam search over the tree to find the best possible implementation. Now, I'll give an overview of the auto-scheduling system as a whole before I describe each component in more detail. As before, we start with the Halide algorithm as input. We perform a tree search over the space of schedules. This operates in two stages. First, it identifies the low-cost stages, makes coarse-grained decisions for them, and freezes those decisions. It then schedules the rest of the algorithm using hierarchical sampling. The search is guided by a learned cost model that predicts the runtime of the generated scheduling options. And using this procedure, we can generate possible schedules for the input algorithm. We compile and benchmark each of these schedules to obtain ground truth runtimes. We can then retrain the cost model and repeat this process. After each training iteration, the cost model ideally becomes better at predicting runtimes and can guide the tree search into better parts of the scheduling space. Now let's start by looking more closely at the tree search. I'll first explain how the basic form of the tree search works, then describe the hierarchical sampling strategy, decision freezing, and memoization. We have the same example 3x3 blur from earlier. Our goal is to generate a complete loop nest implementation, and we do this by scheduling each stage of the algorithm one by one. We always start making scheduling decisions from the end of the pipeline and work backwards. So we start with blur y, then do blur x. For each stage, we need to make two decisions. The first decision to make is, where in the loop nest should it be computed? And second, how should it be parallelized? This approach mimics the way a human expert might schedule an algorithm, by first making a coarse-grained decision, followed by a more fine-grained one. Underneath the algorithm, we have displayed here the current partial loop nest representing the schedule, which is initially empty. The first decision to make is, where in this partial loop nest should blur y be computed? And since the partial loop nest is empty, there is only one option, which is to create a new loop nest that will compute blur y. So our search tree will generate a single new node. At this point, we run the cost model to predict the runtime of the new option, and then we select the best one. The second step is, how should blur y be parallelized? This will produce potentially thousands of options for different tilings of the block and thread loops. We run the cost model again and take the best option. At this point, blur y is fully scheduled. We then repeat this process for blur x. We generate possible locations where blur x can be computed. We run the cost model and we take the best option. Choosing how to parallelize blur x is straightforward now. It's already inside a parallel loop, so it doesn't need to be parallelized. So that leaves only one option left. We can run the cost model one more time, and the algorithm is now fully scheduled. As I mentioned before, some of the decision points involve potentially thousands of options. Featurizing and evaluating states with the cost model is very expensive, so for scalability, we want to avoid evaluating all of them. But how do we choose which ones to evaluate? We want to stratify the search space to include a diverse set of promising options. At each decision point, we group all the schedules into buckets based on structural similarity. We expect that schedules within the same bucket will have similar performance characteristics, so there's no need to evaluate all of them. Instead, we sample representatives from each bucket to be evaluated and discard the rest. Using this approach, we ensure that there are structurally diverse options for us to consider. We define structural similarity as the loop nest structure up to a given depth. Here we have two different loop nests, but if we consider their structure only up to depth 1, they match and will be placed into the same bucket. But for a depth of 2, the same loop nests no longer match, so would be placed into different buckets. Since they match at depth 1, but not depth 2, these loop nests have coarse-grained similarity, but not fine-grained similarity. In practice, we run the tree search with multiple iterations, increasing the depth each time. In the early iterations, many schedules are structurally similar, which creates few buckets. So these early iterations identify promising coarse-grained structure. The later iterations create more buckets and focus on refining fine-grained structure within the earlier identified candidates. At the very beginning of the tree search, we run the same procedure, but only consider limited scheduling options. The search evaluates these options as described earlier to produce a final schedule. The lowest cost parts, as identified by the cost model, have their decisions frozen. We then run the tree search on the important parts of the program using the full scheduling options, effectively focusing our time on scheduling the important parts of the algorithm. This mimics how a human expert would make quick decisions for the less important parts of the algorithm so they can spend more time on the important parts. During this entire process, many partial schedules frequently reoccur. For example, we might schedule blury in its own kernel and compute its featurization. Then if we were to schedule blurex in its own kernel, we don't want to recompute the features of blury again. So we always memoize featurizations after they are computed and then reuse them. And this includes not just for kernels with a single loop nest, but also for kernels with nested loops, where in this example, the featurizations for both blury and blurex are memoized together. Now let's look at how the cost model works. Our goal is to predict the runtime of schedules. In order to be able to consider a large number of potential options, we need to make decisions very quickly. Compiling and benchmarking every option is much too slow. We could try some kind of end-to-end learning, but we actually tried learning features automatically from loop nest structures, but found that this required a network with large capacity and was also too slow. We could try using a hand design cost model or heuristics, but with these, it's difficult to get good prediction accuracy. Instead, we use a hybrid learned hand design cost model. We use Halide's built-in analysis tools to compute a set of features from a loop nest and combine them with a hand design model that includes terms that we expect will be predictive of runtime. Some of the features include the number of values computed, the number of threads used, the number of blocks used, the size and location of memory allocations, and 65 other features. We pass these features into a small neural network. It gives as output a set of learned coefficients, which are weights on hand-designed cost terms, each of which is computed by combining the features in various ways to capture things like compute cost, cost associated with idle threads and low occupancy, load cost, store cost, and so on. We sum all the weighted terms to arrive at a runtime prediction. The network takes as input some algorithm features, which are operation counts, for example, the number of floating point multiplications, and embeds them. It does the same for the schedule features. It then stacks them both together and uses the fully connected layer to make the final prediction. Using these components, it's possible to generate schedules for a given algorithm. But if we compile and benchmark these schedules, we can also retrain the cost model to refine its ability to make good predictions. So how do we actually generate training data for this process? We use a combination of random pipelines, which are randomly generated combinations of common image processing components like convolutions, upsamples, downsamples. And we also have a set of 17 real-world test applications. Each of these applications is trained in a hold one out fashion. So it's trained on all of the random pipelines and all of the other applications, but not itself. And we use the autoscheduler itself to generate schedules for this training set. Now let's look at some results. Using the freezing and hierarchical sampling, the number of states that are evaluated is greatly reduced. For the test set, on average, we evaluate 5% of the total states, and in the best case, fewer than 1%. And this reduces the compile time by an average of 85% and up to 97% in the best case. The reduction in the number of states evaluated is larger than the reduction in compile times because memoization reduces the marginal cost of more state evaluations. And the schedules that are produced are on average 1.24 times faster with hierarchical sampling and freezing than without. Here we have the relative performance of the produced schedules. Blue is the state-of-the-art GPU autoscheduler, and red is a human expert. Our autoscheduler can produce schedules quickly that are 1.07 times faster than the baseline. If you spend a few minutes compiling and benchmarking 5 of the top candidate schedules, we see a speedup of 1.3 times. And if you spend tens of minutes compiling, benchmarking, and retraining the cost model in an auto-tuning loop, the speedup is 1.66 times over the baseline and approaching human expert level. It's worth mentioning that the human expert in this case was actively trying to beat the autoscheduler. Each time the autoscheduler found a schedule faster than the existing human one, the expert would spend more time, in some cases several days of concentrated effort, trying to beat the automatic schedule. So we consider this a high bar. This talk describes an algorithm for automatically generating high-performance Halide schedules for the GPU. The key ideas of hierarchical sampling, decision freezing, and memoization make it possible to explore a large space of schedules efficiently. We hope that these scalability strategies provide useful inspiration for other array-based compilers beyond Halide. And the code for the autoscheduler will be released as open source soon, We encourage everyone to check it out. Thank you.